All right, so what I'd like to talk to you today on this video segment is the use of an X-ray fluorescence detector in the studies of metal pollution in mine soil. So this was a machine that ASU acquired after I had started teaching the class, but it is so useful in these kinds of classes that I thought I would give a little bit of a video about it so that you could see how much easier this can make some of the kinds of research that I do. This is not the world's most expensive machine. It runs about $70,000, but I understand that's far more money than many people have to spend. So if this is not available, what I would actually recommend is perhaps try to collaborate with some of your colleagues, both at your institution and at neighborhood institutions. National Science Foundation oftentimes has grants for large research equipment among shared facilities, and this is a way that you can actually get something like this that can be used then in multiple locations or by multiple groups. So X-ray fluorescence detectors work by passing a beam of X-rays through a sample and then recording which parts of the frequency have been reflected and in what intensities. If the machine is calibrated correctly, it can actually detect almost every metal element in your sample. And what's really neat about that is the amount of prep work is vanishingly small. So I'm going to go ahead and prep a couple of soil samples here for you. I'm going to show you a sample from one of my colleagues and my colleague and wife, Jennifer Foltz-Sweat, who you've also seen in these videos. Some of her research I want to show you, and then I want to show you one of the plants we use here. So let's get started. So these are the sample cups from the X-ray fluorescence detector. You'll notice they are open at both ends, and you have these rings. So these rings are going to hold a piece of plastic wrap over the cup so that it holds it in. And the plastic wrap, there's two different types of plastic wrap that the XRF company makes. One of them is called microporous thin film. The other one is a Prolene thin film. The microporous thin film is the expensive one. And the reason it's so expensive is it has to be able to allow water to escape. When we put the samples in the X-ray fluorescence detector, it will actually bring them to a vacuum so that atmosphere is not interfering with the sample analysis. This means your samples must be dry before they go in there. So let's start using a little more plastic than I need to just to make it visible. So we're going to put a ring over the bottom. All right. So that gives our bottom. Now in this case, what I want to do is I want to make a soil sample. So let's take some soil that we sampled outside when we were looking at how to do field work. And what I'm going to do is I'm going to just take a little bit of this. Probably be a little neater than this, but the process gets messy. So there we go. Let me get that big piece of wood out there. So you put some soil in there. What you're then going to do is take your microporous film. It's easy to tell these apart. Microporous film is white and opaque, whereas the Prolene film is clear. Putting that down here. Now, one of the interesting things about it is they put a cutter on this film. They do not put one on this film. I'll take my handy scissors here. All right, now we want to put this over the top. I want to put a ring on it. Now, as you can tell, I'm going to knock the dirt. So the next thing you have to do, and commonly this is really what has to happen with undergraduates because they're not generally the neatest, is you want to clean all this dirt off of it so that it doesn't get in the XRF. Then, if you want to make your sample look nice, you can go ahead and trim off the excess film. If you do get one of these machines and students start working in them, you're going to be amazed at how quickly the students figure out how to use far less film than what I just did to make their sample. Let me get that last piece of film cut off there. There we go. And so this is our sample. Now, got to make sure it's completely sealed, which it is. Now, how many of you have ever worked in chemistry? You're probably sitting there right now saying, Ken, you didn't take the data you need. I actually did. So what most of you are thinking is, I don't know how much this weighs. I don't. And that's the beauty of XRF. I don't need to. Because the X-ray fluorescence machine actually returns a percentage data. In other words, the percent of your sample that is aluminum or iron or lead or copper. We don't even have to weigh the sample. So this is how you would do a soil sample. In my work here in Arizona, one of those common pioneer species, or weed, however you want to call it, that we encounter is this one here. This is Malva parviflora. Perhaps some of you recognize it. It grows throughout most of the United States. It's actually an introduced European weed, but it's really common in disturbed areas. And what my students have done in one of their other research projects is they take the plant. Now, obviously, we're not stuffing this plant into this cup. There's got to be some more processing here, and I don't have the time to show you all that. But what you're going to want to do is you want to dry that plant up. You want to grind it into a nice powder and fill it in the cup. And what I have found here in Phoenix that works great for me is I can leave things out on the countertop, and within a week they're dried out. If that is not possible for you, you're going to need to find some sort of desiccation cabinet or drying cabinet or some way to dry them out. Once they're dried, you want to grind them into the powder. And the easiest way we found is simply buy a coffee grinder, $20 coffee grinder from a local department store. You can grind that into a powder and prepare a sample cup just like this. The final cup I wanted to show you is, and this came from some experimental work, like I said, my wife was doing, but as you can see here, you can actually put a whole organism into one of these cups. Now, I don't recommend this, and here's why. The sensitivity on the XRF is about down to 1 part per million, that's it. And given the very little amount of weight here, it's very difficult for the XRF to detect anything in this insect unless it was in real high amounts. But if you had reasons to suspect that this insect might have been poisoned by a metal, say arsenic, which is technically not a metal, this would be one way to do that. So this is how you do sample prep for the XRF. What I want to show you now is the machine and how we load our samples into it. Thank you. All right, so I brought you into the bowels of ASU West Campus's science department to show you my X-ray fluorescence detector. So this is the X-ray fluorescence detector here. It is connected to its own PC. A little bit of advice, in our department, most of these high-end research machines we have, the computers that run them are not hooked to the internet. And the reason why is that we don't want some update of Windows to render the software that runs the research machine incompatible. And this does happen, unfortunately, at a rate that is high enough that makes one concerned about it. So for a lot of these high-end research machines here at ASU's West Campus, we keep their PC that's controlling them off of the internet. All right, so how are we going to do this? Well, here is where we load our samples. Now you'll see there's a tray of 20 here. I've already brought in, as you can see, the bee that I showed you before, as well as our soil sample. So you're going to want to make sure when you put them in, you put the clear side down into your XRF. Come over to the software. I've got a list here, and then you would actually push the green button and get it started. I'm not going to do that right now because we don't want to run this analysis right now. But what I would like to show you is what that output looks like. So this is output from a typical sample that research students of mine have done on soils from gun ranges. And in this case, what my students are looking at are actually informal gun ranges. These are places that people go into the desert to target shoot. What the software is going to put out, and again, this all depends on how you program the software. You can actually focus on a smaller number of elements and run a more in-depth scan, or you can look at an entire suite of elements, which is how my research students started. So as you can see, we have our elements here. Parts per million. The software can be set to detect at parts per million, as well as a standard error. This way you can actually calculate things like your coefficient of variation and the like to decide if that covariation is too high. You may not think that the data is trustworthy, and that's usually what happens when you are detecting things at the very limits of detection. However, when you look at something here like, well, calcium is very common in the calcium carbonate-based soils here in Arizona. So this one has over 22,000 parts per million, so that's pretty reasonable. But this is the kind of data that comes out of it. It is an Excel file, so you can bring it to your students immediately and get them working. And honestly, this type of technology is really optimal for working with undergraduates. This machine requires no toxic acids or the like for sample prep. If any of you are familiar with inductively coupled plasma mass spectrophotometry, which is generally the state of the art in measuring metal in samples, the preparation for that involves very toxic acids like nitric acid, hydrochloric acid, and hydrofluoric acid. We avoid all of that by using this X-ray fluorescence detector, and really it is a wonderful machine to use in undergraduate research. That's what I wanted to tell you about my detector. Thank you for listening, and I look forward to speaking with you in the question and answer session. Thank you.